We have Ewan Wakefield to talk to us about the importance of changing Antarctic sea ice habitats to albatross and petrels. Let me change these. To change these. Because you are using PPT, right? PowerPoint.
Yeah.
Okay. I think, yeah, sorry.
Okay. Do I use the mouse or?
You can use it both. If you have something to show, okay, you can use the mouse.
Right.
Yep.
Right. Hi, folks. This is the first time I've done a talk for about a conference for about 6 or 7 years. So be kind to me. Yeah. So I'm going to actually talk about a couple of studies here. So I'm going to race through this fairly quickly. Just some definitions about sea ice. The sea ice around Antarctica covers about 20 million square kilometres when it's at its maximum, which is around about September, early October. And then as the summer progresses, that shrinks back to about 4 million. So that makes it one of the biggest habitats, or biggest seasonal habitats on Earth. It's about twice the size of Canada. The way that sea ice is kind of monitored, I guess, is using satellite radar systems. And the product you get from that is a percentage sea ice cover, which is what these plots up here show. So there's some kind of nominal definitions, like the edge of the sea ice is defined normally as the 15% sea ice contour. So that's the kind of pink line, the blue line you can see on the left plot. And then the seasonal ice zone is the part of the ocean that's sometimes covered by sea ice, but it isn't permanently covered by sea ice. That's the largest kind of habitat, if you like. And then the marginal ice zone is the part of the ice which is affected by wave action. So the ice breaks up there, it's got intermediate sea ice cover, so it's not complete cover. And nominally it's between 15 and 80%. And then the consolidated ice zone is the 80 to 100%, which tends to be near the coast. It's often multi-year ice. Sea ice is really important because it affects primary production, and then that cascades up to higher trophic levels. What we know about flying seabirds in the sea ice, in the seasonal ice zone, and in and around sea ice, largely comes from ship-based surveys, which go back all to the 60s and even earlier than that. But people like David Ainley kind of thrashed this stuff out from staring at the ocean for hours and hours from ships, and he and others came up with this kind of three assemblage paradigm. So you have species that occur within the sea ice, you have species that occur at the ice edge, and then you have species that occur in open water. The sea ice affiliates mostly were thought to come from Antarctica. They breed in Antarctica and live there year-round, so they occur in the sea ice year-round. The open water affiliates were thought to come from colonies further north, possibly non-breeding birds, but the status of those really wasn't known, because this was ship-based observations. And then in the middle you have these kind of ice edge affiliates. Again, not really a lot is known about their provenance. And there's all sorts of open questions about, for example, why would it be that some species are open water affiliates and others are ice tolerant? Could it be, for example, that the open water species can't go into the ice because they're dynamic soarers? So these are some of the kind of holes that I'm hoping this talk is going to fill a few gaps in there. So part one is about species that breed in the subantarctic, 7 species there. Part 2 is about snow petrels, which are an Antarctic breeder. And the first part is in this paper, which is just in press at the moment. So it's a monograph, huge beast of a paper. So I'm just going to dip into some of the kind of highlights, if you like. The aim really was very simple. It was just to say birds breeding in the subantarctic, so this is from Bird Island, South Georgia, 7 species. How much do they use sea ice affected habitats? Because that hasn't been done really using tracking data. And it was using the huge bass tracking data set. But as always, I overcomplicated it, so thrown in some hypotheses. If you want to look at how birds use sea ice, well, they move seasonally because they track resources, and that could be to do with tracking solar insolation. So as the kind of apparent sun moves south, primary production moves south, you get a resource wave, and birds may track that during the breeding season. And they probably also track the ice edge as that recedes. So I won't go into the details of the methods very much, but I tracked about 50 of these birds, but there was about 1,300 tracked altogether since the early 90s. And the 7 species are the 2 giant petrels, white-chinned petrels, light-mantled albatrosses, black-browed and grey-headed albatrosses, and wandering albatrosses. And this is an example of the kind of fairly descriptive results in the paper. Each of these panels is approximately a month, and going from June up in the top left to back down to June or May, June in the bottom right. Wandering albatrosses breed throughout the annual cycle, and you can see that as the year progresses, they move south. And they also go into the seasonally covered ice zone. And if we just look at latitude now, so this plot on the left is like a kernel density plot, a utilization distribution plot, but just using latitude on the y-axis, and on the x-axis we've got time. And you can see that the birds spend most of their time around the latitude of the colony, no surprise there. But if you look at the kind of bigger picture, there's this kind of sinusoidal pattern. And that, we think, reflects the kind of sinusoidal variation in light and therefore primary production. Contrast that with southern giant petrels. They go down into the ice-covered area when it's ice-covered early in the season. And again, if we look at their latitudinal variation, spending most of their time near the colony, but an intercept-only straight-line model best describes their distribution over the season. There's not any kind of sine wave there. So then this is the similar plots for the other species. A few of the kind of highlights there: northern giant petrels, say north of the colony, southern giant petrels to the south, white-chinned petrels, black-browed albatrosses and grey-headed albatrosses also have this kind of sinusoidal kind of migration north and south over the breeding season. Light-mantled albatrosses, they go south throughout the breeding season. Then if we look at how different areas of the sea ice zone are used through the season, the plot on the left shows day of breakup when the ice melts, and on the x-axis and on the y-axis the day of first use. And you can see that for the albatrosses, they're not using the sea ice zone until about about a month after the ice breaks up. So that suggests they're not being prevented from entering that necessarily, but they're not going there until the ice is broken up. There's a phytoplankton bloom that transfers to higher trophic levels, and then they're kind of invading that space once there's a kind of boom in production at higher trophic levels. Southern giant petrels, they're in the ice before it's broken up. And then here's some detailed tracks. On the left, we've got the top row is the kind of wide picture, and then the bottom row is the zoomed in picture. And southern giant petrels, you can see they're making foraging excursions right into the ice, encountering sea ice concentrations up to 100%. Light-mantled albatrosses, they're tracking the ice edge as it melts, but not going into the ice. Black-browed albatrosses, they're encountering high ice concentrations sometimes, but that's probably just an artifact of the analysis. That's because they forage very close to land, and sometimes ice on land can appear to be sea ice in the satellite imagery. The second study, which I really don't have time to go into in a lot of detail, is about snow petrels breeding on the Antarctic continent. They're known to be ice affiliates, almost obligate sea ice foragers. We're interested in their foraging ecology as part of a wider project where we're trying to use the spit from snow petrels, which builds up in deposits, to reconstruct past sea ice climates. But this part of the study was just trying to get at some fundamentals of their kind of foraging biology. So we tracked them with geolocators. So this is from 2 colonies on the left, and the blobs, different colours at different years. The top panel there is pre-breeding, so that's about a week before the start of breeding. The bottom panel is pre-laying exodus, and then we've got brood guards and failed breeders. And basically you can see they following the ice edge south. If we zoom in using GPS data to the kind of core breeding period, incubation, brood guard, and post-brood, you can see during incubation they're going very far out to the ice edge. As the ice melts, which is that contour across the middle there, they're very close to in brood guard, very close to the coast. And then in post-brood, when the ice recedes right down into the Weddell Sea, they're following it down there. And so again, we get this kind of relationship between foraging latitude and the latitude of the ice edge. So they're basically tracking the ice. And then what I'm doing at the moment, or what I've been doing recently, is fitting habitat selection models to the different periods. So this is for the snow petrels from December through to January. And you can see that if you look at sea ice concentration, early in the breeding season, they're favouring fairly light sea ice cover. And as the breeding season, so this is the second row, as the breeding season progresses, they favour those intermediate sea ice concentrations, and they track those all the way across the breeding season. You can ask me about the other details on here at the end of the talk if you're interested. So to fill in some details, some conclusions, yes, snow petrels are associated with sea ice, but they track it through the breeding season, and they also have a kind of, as the ice recedes, they have a lagged response where they start switching from using sea ice covered areas to recently opened areas, which says something about what they're feeding on probably and how they're feeding. Southern giant petrels commute all the way from South Georgia right down into the sea ice. They're probably foraging, we think, on placenta and seal placenta and carrion from seals pupping on the sea ice. Light-mantled albatrosses, they're foraging, tracking the ice edge but not going into the ice. And the other albatross species and white-chinned petrels, they're coming into the seasonally covered ice zone, and they're using it quite a lot, but only after a lag. So all of this adds up to these species ecology, even though the subantarctic breeders are not breeding in Antarctica, they're probably strongly affected by sea ice dynamics. Why does that matter? It matters because, well, we know Arctic sea ice has been declining for years, but it's always been, until recently, thought that Antarctic sea ice cover wasn't declining. But in the last decades, we've had a regime shift, and Antarctic sea ice is on the way out, unfortunately. This is just from our study sector. This is the seasonal amount of sea ice, and you can see that the ice is breaking. The last few years, it's been breaking up earlier, and that green line, it should actually say 23, 24. The sea ice has reached a record low. It's never been that low before. So I will leave it there. Thanks.
A couple of questions to you. Yeah, there, down there.
Thank you. With the southern giant petrels, during the breeding season, males and females tend to have different diets.
Yeah.
Were they both going down to the sea ice?
They were, but it was dominated by females, yeah, as you might expect.
Yes.
Yeah. Other question? No? You can catch up with you on the coffee break, maybe? Yeah, thank you.
Okay.
So next we have Kristy Laurenson. that will talk about how winter storms impact seabird survival and demography. This is not working anymore. Maybe the batteries. Yeah. Okay. It was just out.
Thanks very much.
You talk there? Okay. So I will.
Is it-
No, you can talk there if you want.
Yeah, that's fine.
Yep.
Yeah. Okay. Yeah. Okay. Cool. So hi everyone. My name is Kristy, and I'm talking to you today about some of the work that I've done for the first chapter of my PhD. So we all know that climate change is having big impacts on ecosystems, and one impact is that climate change is altering storm patterns globally. In the North Atlantic, what is expected is not a change in overall storm numbers, but an increase in the frequency and severity of the most extreme storms. And we all know how damaging storms are for us humans and our society and our infrastructure, but the impacts on wildlife and seabirds aren't quite as well known. And you might think that it's really obvious that seabirds must be at risk from storms, because if you go for a walk along the beach after a really stormy period, you might find lots of seabirds washed up dead on the shore. And these deaths can be like mass mortality events, and as Maite already told us, there was a mass mortality event in 2013-14, and as she said, there was about 50,000 birds found washed up dead along the shores of northern Spain, France, and the United Kingdom. And these mass mortality events could be catastrophic for seabirds, because in seabirds, which are long-lived and slow to reproduce, adult survival is the most important parameter for regulating population size. But the population level consequences of storminess aren't really very well known for adult seabirds. Previous work has shown that adult seabird survival is correlated with positive indices of the North Atlantic Oscillation. And the North Atlantic Oscillation is basically just the measure of the pressure difference between Iceland and the Azores, and positive indices of the NAO are correlated with stormier periods in the North Atlantic. However, this basic measure of pressure difference can't tell us anything about individual storms or clusters of storms or anything about the characteristics of storms. And as you can see, the North Atlantic Oscillation is actually correlated with storminess in very specific regions of the North Atlantic, which is shown in orange. So this is where my PhD comes in. I want to try and understand the impacts of storms on adult seabird survival using actual storm data. So to do this, I'm looking at the impacts of storms on these three species: common guillemots, Atlantic puffins, and razorbills. And these three species are good species for looking at the impacts of storms on seabirds, because they're quite closely related, but they have some differences in their morphology, breeding strategy, and wintering strategy, so they're good for comparing and contrasting storm impacts among species, and they're also quite frequently found among seabird wrecks. These three species have also been the subject of a long-term capture and recapture study that's been going on in Coimbra since the 1970s. Coimbra is marked by the location of the yellow star, and you can see that it's just off the coast of Wales in the Celtic Sea. So first off, I need to know where these birds are going in winter so that I can get storm data for the most appropriate area. And conveniently for me, some of my co-authors have already tracked guillemots and puffins from Coimbra over winter using geolocators. So I got my hands on that geolocator data, and I estimated the 90% utilization distribution and used that as their wintering areas. So that's what's plotted on the map. We've got the wintering area for guillemots in green on the left, and the wintering area for puffins in blue on the right. Razorbills haven't been tracked over winter from Coimbra before using geolocators, but other tracking studies at other UK colonies have shown that razorbills have quite a similar winter distribution to guillemots. So that's what I've assumed is the case here, and I've just assigned the same wintering distribution for razorbills. I should mention I'm defining winter as December to February because this is a meteorological winter, and this is when storms are most frequent and most intense in the North Atlantic. So now that I know where these birds are going, I need some storm data. So again, with the help of one of my co-authors, Matt Priestley, who works as a meteorologist at the Met Office, we extracted storm data from the European Centre for Medium Range Weather Forecasting's ERA 5 climate reanalysis dataset. And what climate reanalysis is the combination of current weather forecasting models with previous weather observations, and you can basically recreate past weather conditions. So for those wintering areas I've just shown you, we extracted the total number of storms per winter, the mean storm intensity and minimum sea level pressure, the mean storm duration and the gap between storms in hours, and the number of days that exceeded different wave height and wind speed thresholds. Now these were all correlated, so I couldn't combine them together in models, so what I did instead was a principal component analysis, and I extracted the first principal component as my main storminess covariate. So high values of principal component 1 represent stormy winters, and low values represent calmer winters. And from now on, I'll just be calling principal component 1 storminess. So now we just combine all that information together, and I'm using Carmack-Jolly-Siever models to estimate adult survival, and a Carmack-Jolly-Siever model is a model that's been specifically developed to estimate survival rates from mark recapture data. You can also include covariates on Carmack-Jolly-Siever models. So obviously my main storminess covariate is my main covariate, but I'm also including population size to account for any density-dependent impacts on survival, and I'm including sea surface temperature to account for any food supply impacts on survival. So on to some results. What did I find? Is survival correlated with storminess? Well, storms reduce guillemot and razorbill survival. So I'll just talk you through these graphs individually. We have storminess on the x-axis with stormier winters represented by higher values, and survival on the y-axis. And guillemot survival is negatively correlated with storminess. There's also a negative correlation with summer sea surface temperature, indicating that guillemot survival is probably also impacted by food supply impacts, which isn't really surprising. We see a similar pattern in razorbills. So again, razorbill survival is negatively correlated with storminess. There's also a significant interaction with population size. So in stormy winters, where the population size is larger than average, the impact of storminess is higher, and that's shown in this graph in the dark red line. So in stormy winters, survival is even lower than normal. On the other hand, puffin survival wasn't really related with storminess at all. Instead, the main driver of puffin survival seemed to be winter sea surface temperature, indicating that food supply impacts are probably the most important for puffins. And together, these results show that guillemots and razorbills are probably more at risk from storms, especially under future climate warming if sea surface temperatures continue to rise, but also possibly if the razorbill population on Coimbra continues to grow. So next, I looked at the impacts of these storm variables separately to see if I could figure out what was driving the relationship between storminess and survival in these three species. So again, we'll go through the graphs one by one. First off, the variable that was most correlated with guillemot survival was the number of days exceeding 35 meters per second wind, which is on the x-axis. And again, guillemot survival is negatively correlated with that variable. We found a similar relationship in razorbills. So again, razorbill survival is negatively correlated with the days exceeding a 30 meters per second wind speed threshold. And that significant interaction with population size was there again. So again, when population size is higher than average, the impact of wind speed on razorbill survival is also greater, and you have lower values of survival, again shown by the darker red line. For puffins, although there was no overall storm impact before, I still looked at the impact of these different storm variables. And what I found was that puffin survival was positively correlated with the mean gap between storms. So when storms occur more spaced out, or there's fewer of them overall in a winter, puffin survival is higher. There was also a significant interaction with winter sea surface temperature, which is shown by the dark blue line. So when the gap between storms is short, and when winter sea surface temperatures are higher, puffin survival is lower. And again, overall, these results suggest that guillemots and razorbills are probably more at risk from the projected changes in storminess in the North Atlantic, because although we don't expect a change in the overall number of storms per winter, what is expected is an increase in the severity and frequency of the most intense storms. So if wind speeds exceed these thresholds more often, guillemots and razorbills are probably going to be more worse off. And while guillemots and razorbills seem to be more at risk from storms than puffins do, at the moment, current storminess levels are having quite modest impacts on populations, on Coimbra anyway, because the population size of all three species has increased over time on Coimbra. So the population size is shown by the solid black line, which is going up in all three species, and survival rates over time, although they fluctuate, population size is still going up. And the survival rates are shown by the dotted coloured lines. So I'll just finish up to reiterate some key messages. Storms reduce guillemot and razorbill survival, while puffin survival doesn't seem to be impacted by storminess very much. You can use specific storm characteristics as predictors of seabird survival, but these vary among species. Guillemots and razorbills might be at greater risk from future storminess that's expected in the North Atlantic than puffins, but at the moment, current storm impacts seem to be quite modest on these three species. So all that's left to say is thanks very much to my supervisors and to my co-authors for sharing their data, and thanks very much to the many, many field workers that have collected this data since the 1970s. Thanks very much to the conference organisers for asking me to do this talk, and thanks very much to you all for listening.
So, time for questions. Yeah. Couple of them, 3.
Thank you. Do you have an hypothesis?
Yeah, thank you.
Does it work? Yeah. Yeah, thank you. Do you have an idea why you see this density dependence effect for the razorbills and not for the guillemots?
So we think that all three populations are increasing on Coimbra because they were previously persecuted and because of chronic oiling after the Second World War, with all the ships that were sank and all the oil that they were just churning out over the years. But they're now on the up, they're all still recovering. Guillemots breed at a much higher density than razorbills, so I think maybe the razorbills might be sort of getting closer to the carrying capacity of Coimbra maybe compared to the guillemots, whereas I think the guillemot population is about 30,000 on Coimbra, and previously it was estimated about 100,000, so the guillemots have still got a long way to go, and the same with the puffins are still increasing as well.
Thank you, very nice presentation. So I wonder if you will have a look, or you have had a look already, to the juvenile and immature survival. Do you have any idea
so
about?
I'm currently working on that at the moment just for guillemots. It's quite hard to identify a signal for juveniles because obviously that fluctuates so much anyway. But between us and the conference, because it's not published yet, at the moment I'm seeing the strongest relationship between juvenile survival and autumn storms. So possibly when juveniles first become independent after, because obviously there's paternal care in guillemots after they leave the colony. As soon as that paternal care ends, and if it's stormy, I think that's when juvenile guillemots are probably most at risk.
Hello, thank you very much for your talk. Something that I might have missed, I didn't understand in the Atlantic puffin, what's the mechanism with greater survival and greater gaps between storms? How are these two connected?
So yeah, I suppose it's quite a weak relationship, but so the gap between storms is measured now, it's just how far apart storms occur.
Yeah.
And survival's higher when there's longer gaps between storms. It's probably because if a storm occurs, they've got time to refuel, get food on board before the next one comes, and they can sort of weather the next storm.
Okay, that makes sense. Thank you.
Okay, let's go. Next one.
Thanks
Thank
very
you.
much.
So next we have Ella Sophia? Oh, no, Sarah Bond, sorry. Sarah Bond. How North Atlantic marine heat waves affect behavioral responses of Manx shearwaters, breeding Manx shearwaters? Yeah, thank you. Sorry. I can skip this one. Okay, so you know front, back, you want to buy here or here? No. So let's put this a bit.
Hello, I'm Sarah. I'm currently a postdoc with Oxnard Research Group, which means that I'm based on Skomer for 5 months of the year, studying Manx shearwaters. Luckily, Kristy told you where that is because I completely forgot to include that. So it's off the southwest coast of Wales, and that's at the biggest breeding colony in the world. So I was going to start by telling you a little bit about the structure of the long-term study, because all of the data that I'm going to talk about has come from this, and I will give you a bit of insight as to why we were interested in the marine heat wave. Sorry. So the research group has been studying Manx shearwaters on Skomer Island since 2006, where we deployed our first loggers, GPS loggers and geolocators. And then we started more intensively monitoring breeding success and timing measurements in 2009. So this is a long-running study that's very targeted to following the outcomes on individual burrows. And so it's very high-resolution data when you delve into it. And so we have the Manx shearwaters from about March, but before they arrive with us, they're they're wintering off the coast of South America. And then in March, they head back up the coast and then over the Atlantic back to the UK. And so once they are back at the colony, they are spending about a month hanging around, getting in their burrows, meeting their partners. And so we arrive at the same point and start monitoring the burrows for egg laying. Egg laying occurs over a month. The birds are breeding in burrows, so we can check them every day. So we collect lay date, and then we also collect metrics about weight, length, and width of the eggs to see if we can detect some changes there. And then we leave them alone for most of the time, and we just start checking again to get hatch date once we get towards our predicted hatch date. During incubation, we're also deploying GPS loggers, and so every year we're doing a consistent tracking campaign, and this is combined with other islands, but for now, in this talk, I'm just going to talk about Skomer. That's because we have the highest resolution data to tie it in with the breeding season. And then once the chicks hatch, we get a hatch date, of course, and we then have the lovely job of weighing them every day. The chick rearing period lasts about 70 days, so we weigh all of the birds in our colony for 70 days each. You get very familiar with them. And we also conduct some more GPS tracking at this time. And then once they get close to fledging, we will be having peak mass and fledge date, and then we should get some measure of productivity as well. So you can see that we're very involved with observing what's happening on the colony, and this, I would say, is both a blessing and a curse. Once the birds are leaving, so they're heading off back down south in September, we're also tracking them with geolocators. And those geolocators are staying on throughout the breeding season, so we can also use the immersion data to infer things like visitation to the colony. And the reason I'm telling you all of this is because last year we had a marine heat wave in the Northeast Atlantic, which you can see as the black line, which is far beyond anything that has been experienced since records have been collected. This was not something that we were aware of, but it hit the news in June, and that was about the time that we had been thinking, it feels like a bit of a weird year here. And so I should say that this talk is mainly to do with quantifying this hunch that we were having an odd year and seeing if any of the long-term data would back this up. So in terms of how hot it was very hot. You can see on the right-hand side, the bar is just so far from what is normally observed. And inside the box is the extent of the data that we've been working on the colony for. So which we might be able to expect to detect a change, and obviously this is 2023. So I should highlight that we're expecting, if we did see something strange, for it to be a really large effect. And so some of the things that we were observing was that the distribution of lay dates seemed a bit odd. It was very stop and start. Normally it's like a steady increase and then decrease over the month. And then the egg weights, we had just some very heavy eggs and some very light eggs. So normally an egg is around 60 grams, and we recorded one that was nearly 80 grams. For a 400-gram bird, this is a really big egg. And then we also observed a lot of neglect straight after lay. And then once we started tracking, we were thinking that the birds were closer to the colony. They were still going on very, very long trips, but it seemed like they were visiting a lot of areas. And so there's lots of ways that a marine heat wave might be affecting the birds. But the ones that I'm going to talk about here are the ones that sort of link to the patterns that we observed. And so the marine heat wave was caused by a reduction in wind speeds across the North Atlantic, and that has effects also on the oceanic currents. And so this is really important for seabirds because we know that they tend to forage in predictable upwelling areas. And so if you're reducing the strength of the currents, you're increasing the stratification, which means that the foraging areas might be less predictable or less productive. And in Manx shearwaters, we know that they're very reliant on the Irish seafront, so you can see that as the green dotted line that comes below the Isle of Man. And this paper from 2015 showed that this area is really important for all 4 shearwater colonies that we were tracking at. And so in terms of productivity, the recorded chlorophyll alpha measures were much lower last year. And so we think that this might be a reasonable expectation of why we were seeing changes at the colony. I should also say that, as Steph talked about this morning, Manx shearwaters are highly affected by wind speeds in terms of how efficiently they can fly. And so I also had the thought that if wind speeds were much lower, then maybe they were having to expend more energy in order to get to these frontal areas, or it was no longer profitable to commit to commuting to these foraging areas because you could just spend that time searching close by. And so this is a little list of some of the variables that I thought would be interesting to look into. They're quite broad brush, but they were trying to get out whether we actually saw real effects or whether these were just anecdotes. And so from colony observations and from immersion data, we were able to look at lay date, egg weight, the likelihood of neglect, and incubation stint length. And then during chick rearing, we have data on chick growth curves, so how steep they are, the number of feeding visits that the adults make, and the chick peak mass, which is a good predictor of recruitment, and then overall productivity. And yeah, that's from geolocator and observation data. And then from GPS data, because we'd also observed some differences in the tracks, I looked at trip duration. I wanted to look at the difference between the proportion of time spent foraging to searching. I thought if they were having to search more, they would have to go to a lot more foraging locations. And then I also wanted a metric of how directed they were in terms of where they were going to go. So I looked at the maximum distance from the colony and divided by the total distance. So if you were a bird that went straight out to one foraging patch and then came straight back again, you'd have a really high number for this. And if you were a bird that went to a lot of different areas, then you'd have a low number for this. And I've just starred the ones that I've actually quantified. And I'm going to present some of those to you. I'm going to give you a spoiler straight away, is that we do not find any heat wave effects. very disappointingly. Apologies for this graph. I managed to overwrite my data this morning. So in mean stint length, we don't find any differences between the different years. The same for neglect. So this measure is the hatch date minus the predicted hatch date. So if birds have neglected a lot, then you expect the hatch date to be a lot longer than the predicted hatch date. No differences in chip duration. No differences in the max distance divided by the total distance. And then I wasn't able to look at foraging time to search time, but in terms of time spent foraging, actually it's 2022 that looks a bit surprising. And so to wrap it up, my first thought is a personal one, and that's that if you are working a field contract, then you probably should not delve into a big look at a long-term data set with many aspects during that field season, because it will drive you mad. Tim, the PI, suggested it might be a lot, and it was. Do we actually have no response? I think this depends on a lot of things. And so sample size, we often track partners, and so I've had to remove half of our data because obviously I'm measuring the same thing in both of them. We could delve into the metrics like with more of a fine-tooth comb, but I think if there was anything obvious, we would expect to see it here. I guess a precautionary thought about extreme individuals when we're observing anecdotes, which is that they are always biasing what you think that you're seeing. And as Sam talked about this morning, maybe we need to have a little look at variance. And then in terms of climate resilience, obviously we don't see any effects of the heat wave here. We track birds over multiple years, so by definition, we're tracking experienced birds. So maybe these birds are already able to cope, and so far, this heat wave has not affected them, and they've just been able to respond. I would say that that matches what is predicted by other studies. So the MEPS issue that came out in June said that shearwaters should be least susceptible to marine heat waves due to the long breeding season and low flight costs, and that they're able to dive really deep. And then in terms of the cumulative effect of the heat wave extended for 400 days, and so it might be that we're just not seeing it yet. And so finally, it came below record-breaking temperatures in April this year, so maybe this is something we're going to see into the future. And then in terms of the cumulative impacts to the birds, these are very long-lived birds, so we could expect that maybe they are able to buffer these costs in the short term, and I mean that year to year, but into the future, they might pay the costs at another time. And then I just have to say thank you to the Wildlife Trust for allowing us to work on SCOMA for so long, the Leverhulme Trust, and then all of the many, many people that have worked on SCOMA and contributed to this data set. It was really great to be able to look into it.
So, time for a couple of questions. Wants to, yeah.
Hi, that was a great talk. I was wondering, so I know with short-tailed shearwaters, after a marine heat wave, they arrive to the colony late and then seem to catch up and lay their eggs on time. I was wondering if you had any information on arrival date or if you hadn't got there yet. And then sort of, sorry, two-part question. The second part was, you said that the laying was a bit stunted, so they sort of stopped and start. Was there a general sort of later shift, or was it sort of around the mean?
So that's really interesting about, did you say short-tailed shearwaters?
Yeah.
So I didn't look at arrival dates because this was like before the heat wave was due to be kicking off, but we have that data, so I could look at it. And then in terms of the laying distribution, basically it would be some days with no eggs, and then some days with loads of eggs, and then some with none, and then some days with loads. And so the median ended up being bang on, as it always is. But then the tail of the distribution was really long. So how to quantify this, I'm not quite sure.
Thank you.
Hi. Thanks for the talk. Okay, can you hear me like that? Okay. Right. So I don't want to add to the madness of trying to understand real time what's going on, and so apologies in advance. But I was wondering, the thing that the egg changed shaped, or that you observed, did you say that it was much heavier compared to other seasons? I wonder if there could be something hormonal going on as well, and if you have any direct measures of stress hormones. And if so, I also wonder if you noticed any patterns in pair bond disruptions. Like, did you observe any birds divorcing more, for example?
So we asked around as to why the eggs might be very big. I don't know anything about eggs. And the consensus was that sometimes it is a sign of stress that the eggs are so large, but we don't have any measures of hormones, unfortunately. In terms of the pair bond, we probably have the data to look into this, but it's a bit of a headache because we have our study burrows that we check every year, and then we have the birds that we can't reach in other burrows. And so in terms of certainty, like quantifying, okay, you definitely have your pair breeding together, that's great. But in terms of knowing they're definitely not breeding together, that's a lot harder to quantify. I think would need some hidden state modeling.
Great, thanks. Maybe a quick question here.
Hi, Sarah. So, have you eyeballed the tracking data yet? Because one of the things we do know from last year and this year is what there's been a kind of invasion of Cory shearwaters and, in fact, loads of southern species. So you might expect the Manxes to be going a bit further north.
Quantifying any location things because I'm not wanting to step on any other people's toes in the group. However, I think in general we are seeing our birds go more south. So previously, if we got a south-going bird, it would be like, oh yeah, that's exciting. Whereas now I think we see like a fair proportion of them going south. And actually this year we tracked one go all the way into the English Channel into Norfolk. So maybe they are coming at different directions to the same place. I'm not sure.
Thank you. So now we have, I think it's Ignacio, yeah, to talk about snowfall-induced catastrophic breeding failure in Antarctica. Okay. Yep. Okay. So, this is one, it's PDF, right? Change these. No problem. No. I think we have to expand here, and then it should work. Yeah.
Perfeito.
No problem.
Muito obrigado. Perdão? Perfeito. Sí. Boas tardes. Good afternoon, everyone. I know we're all very hot and it's after lunch, but don't worry because the short talks are coming. And this is going to be very speedy. We're going to snap out of this, and I'm going to make things even more enjoyable, I'm going to make it interactive. So pay attention. So many of you will remember me from the Cork conference, where, among other things, we decided, I think Alex was saying how penguins are terribly underrated. And I want to actually continue from the Cork conference, where I showed you things like this. I want to tell you what I have been doing since then. 2 years ago, I talked to you about these three species. Sorry, I cut the gentus. I studied these three species of penguins. I studied the Adelies, the chinstraps, and the gentoos. And I studied them mostly around the Antarctic Peninsula and the subantarctic area around the Scotia Sea. And these three penguin species are very similar. They are phylogenetic cousins. They're in the same genus, Pygoscelis, but they are very different. So Adelies and chinstraps both feed almost exclusively on krill in this area, and they're both declining in this area, wink, wink. But Adelies are much more Antarctic than chinstraps. Chinstraps are much more oceanic. And then we have the gentoos, which are the newcomers, which are more of a subantarctic species, and that are introgressing into the Antarctic Peninsula, and their numbers are increasing. These guys are food-feeding generalists, wink, wink. In order to monitor these species of penguins, we have, my supervisor, Tom Hart, has deployed this amazing network of time-lapse cameras, like normal camera traps, around 40 colonies around this area. In total, we have almost 90 cameras monitoring 6 species, but I'm just going to talk about 3. This already, also I mentioned in Cork. And then to finalize, in Cork, I also showed you this very busy plot where I showed you how I studied the phenology of these 3 species, and I showed you how they are changing their phenology at record levels. So we're talking about 15 days per decade, which is unheard of for any vertebrate in the vertebrate world. Okay, and where I left this is that, well, you know, okay, so they're changing their timing of their breeding season a lot. But how bad is that? Because, you know, these actually might be beneficial, that they can adapt to really, really drastic changes. So I looked at breeding success, and this is what I found. So it's actually really good. You know, we're having a breeding success of well over 1. So all of 3 species lay 2 eggs. So maximum breeding success is 2, minimum 0, of course. And we can see, you know, really cool results. We even have a really nice edge of range. I don't know how the pointer works. Oh, with the mouse. We even see some edge of range effect for the gentoos, where the northern and the southern colonies are a bit lower. You know, really fun stuff. So that was 2 minutes or 3. I think I can go home and have more coffee time. However, let's plot this a different way, because let's see how this has been evolving year by year. And actually, we see that in general, it's still pretty good. But actually, if we look at all of the years in which we have a breeding success below 1, we see several fun things. And it's like, well, there are actually quite a lot of years under 1. Like, this did not show in the box plots. Rubbish. And also, we see that the most Antarctic species have less years below 1, although we do have less data for the Adelies, than the others. So what is happening in these years? And actually, I found that there is something really very particular happening. But the first, I need to tell you a little bit more about penguin biology, especially from these 3 species. And these 3 species nest in Antarctica on rock nests. And you will say, but the rocks are very hard. That's not a fantastic nesting material, but it's the only one they have. And it's a wonderful nesting material for letting the water, the melt water from the snow and from the ice pass below the egg and not touch the egg and not get it hypothermic. So the better nests that you have, the better that your egg will be insulated from the meltwater going under it. This is an image of the colony quite late. The necks are not there, but you see like they do need to nest on snow-free ground. And I'm telling you this, sorry I gave the surprise away, because lately this is what we are seeing. And this is part of the interactive bit. How many nests are here? Okay, you have 10 seconds. You have 10 seconds to think. Okay, hands for 5, hands for 10, hands for 15, hands for 20, hands for 25. Hey, was that up or was it not? Hands for 30. Okay, hands for more. Okay, so there were 20. I'm going to show you. This is an image of several weeks before in the season. This image that you're seeing here, the one where you actually see the penguins, is from the last day before a snowfall came. And it started snowing, and it did not stop for a full month. This is unheard of. We have 15 years of data in our cameras. We have never seen that in any well, we are now seeing it, but again, I'm ruining the surprise. And next part of the interaction of the interactive part is like, how many nests survived? Of all of these that you're seeing here, how many nests raised a chick? So I'm going to go 100%. Okay, 75. I love the optimists. 50. Okay, 25. 10. Oh my God, so pessimist. And 0. Okay, so no gentoos made it. And the chinstraps, only half of the nests managed to raise a single chick. This is essentially catastrophic failure. And unfortunately, we don't just see this in chinstraps and gentoos. We also see it in adelies. Just in the interest of time, I will not do the game again. But this is more or less how it looked like, the same colony. Before, during the snow, that you can see the adelies covered in snow completely. Like there is like 60 nests down there that we monitored. And this is, down here you have the result. You have how many chicks survived all of that, which is just literally a handful. And adelies are Antarctic, considered fully Antarctic penguins, as much as the emperor, because they withstand almost the same temperatures, just that they breed in summer, not like the emperors. So this is quite bleak, but it can get worse. Because now with the increase of temperatures, just a change of 1 degree, which doesn't sound too much, but again, if you change that degree around 0, water goes from solid to liquid. And this is what liquid water does to the warmest colonies in Antarctica. It literally floods the nest beyond the level of the rocks that are supposed to protect the nest, the eggs, and the non-thermoregulating chicks, and essentially causes not a catastrophic breeding failure, because this one was really early in the season, but if you compare January from that year, so the previous breeding season, with this one, you can see that half of the colony just decided to not even breed that year. So this is like early season affection. So what have I done? Just very quickly, what I did was I did not have time to learn how to use an AI, so I designed a really tacky algorithm to show me how bright my images are, and I can find the thaw date. The thaw is the date in which all of the snow melts, and all of the ground, which is millenary penguin poo, goes very dark with all of the water that has molten, and it normally melts within 1 day, and you can find this very reliably in all of our seasons. So I checked that thaw date, and I checked how many days since the penguins settle in the colony until that thaw date there is per season, and I related that to breeding season. And as you can expect after seeing the previous images, that is really bad, but what I was very surprised about is that it's also very bad in, it already affects them at a very, very short periods without the thaw date. And you will be saying like, oh, but you know, these catastrophic breeding events, you know, in such long-lived seabirds, they are not going to be that bad because penguins live 35, 40 years, so, you know, having one season is not going to be that catastrophic. And it's like, yeah, well, that's true. Unfortunately, we are seeing the frequency of these catastrophic events in our cameras much, much more frequently. And we are really concerned that if this trend continues, or even if it just stays like that, that we have 20 to 25% of our colonies with catastrophic breeding failures, this is going to have a new impact that was a non-issue in 2013, 14, 15. Now is going to be a new thing. So, conclusion, I am very worried. You should be too. But also, I would like, as a take-home message, for you to think of the precipitation, because I know it's a difficult variable to get, but with other technology like cameras and stuff, it's actually quite easy. So please think of precipitation. Thanks to all of our collaborators, because this is a massive data set that I could not have gathered in 1,000 years by myself, especially to Tom, who set this up, and to all of our sponsors, and thank you very much for your attention.
Couple of questions, maybe? Yeah, these two.
Hi, thank you. Thanks a lot. Do you think the reason why Adélie seem less impacted by snow is because of their different phenology compared to Gentoo and Chinstrap, or is it for other reasons?
No, I don't think so. I think it's just because they are much more, that they are much more adapted to snow. And actually, I did not show this, but after the big snow of Chinstraps and Gentoos, both Chinstraps and Gentoos that had failed their nest just left immediately. Adélie stayed for up to 2 months incubating dead eggs in the snow, just trying and trying and trying. I think the phenology is actually I don't think the phenology is going to be an effect, because I compensated for that by studying the difference between their arrival, or their settlement rather, and the thaw date, and so that should compensate for differences in phenology.
Second one, this here? No, here.
Okay. Hello, thank you for your very nice talk. Just a quick question. Maybe it's too soon to say, but did you check the breeding success of the penguins that were affected the next year?
No.
Okay.
No. That's for now.
Thank you. So next we go with the speed questions, speed talks, sorry. Andrés, we talk about global distribution and trends to Puffinus mauretanicus, Balearic shearwaters. Let me change these. Andrés, perdón. Yeah.
Okay. Well, good afternoon, everyone. Thank you for coming. My talk is not going to be that fun, but I will try to do it as quick as possible too. And my name is Andrés De La Cruz. I'm a postdoc at the University of Cádiz, and the work I'm here to present is part of my postdoctoral stay here at the University of Coimbra with a group of ECOTOP. And it's entitled Global Distribution, Threats, and Population Trends of the Critically Endangered Balearic Shearwater. Probably most of you know very well the species, but just a quick introduction. Balearic shearwater is an endemic species that only breed in the Balearic Island, and today is the most endangered seabird in Europe, with almost 4,000 breeding pairs and a 3,000 total population of individuals. As many seabirds, they are very low productivity seabirds, and the main threats in land, it's introducing mammals, and at sea bycatch. So with this data, there's some demographic studies that said that the population decline of the species is every year about 10%, and is expected to be extinct in the next 60 years. Then the Balearic shearwater has been studied partially, sometimes in the Mediterranean during breeding season, and sometimes in the Atlantic during wintering, but always with a limited time, and sometimes also with just a few birds tagged with the remote GPS. So under this situation, we try to give an overview, global distribution, going beyond the known areas, to trying to identify the variables that drive the distribution of the species, trying to give a population trend in and out of the Mediterranean, and trying to overlap the core areas, the key areas, with the main threats, and also the protected areas to try to know how well protected are the species. How to do that? Well, we gathered to collect data from many different institutions, and finally we got 20 years of data of at-sea counts from oceanographic campaign vessels along Europe from 10 different countries. And then we got the spatial distribution model using generalized additive models, comparing abundance versus static and dynamic variables, such as distance to coast, distance to colony, productivity, micronectome, the most common variables. Also, we're trying to get the trends using generalized linear models versus abundance versus years. And then we identify the most important areas, and then we overlap with fisheries using global fishing watch data, offshore wind farms, and finally with marine protected areas. The results, as we already knew, the distribution of species is very coastal around Iberian Peninsula and also west coast of France. And the distance to coast, bathymetry, and sea surface temperature were the most important variables to predict this distribution. No. And then the most important key areas in the most important key areas in the Mediterranean are in the east part of Spain, along Catalonian and Valencia coast, around the Balearic island, and in the Atlantic, the Gulf of Cadiz, and also south of Portugal. But in the Mediterranean, we found new areas with a very good habitat suitability for the species in the East Mediterranean, west coast of Portugal, even west coast of Sicily, and north of Africa. And also we got some new areas in the Celtic Sea, and also some other places in the coast of UK, which is in line with the previous study indicating the species is moving and expanding north. But maybe the most important results of this study is the population trend. We found population trend declining dramatically, very strong negative decline in Mediterranean and also in the Iberian coast, but a strong, even exponential positive trend in North Atlantic, which we can make that is probably a compensation, but if we check the y-axis, we can see that it's 100 times less. So that means this is not compensating the main losses in the main area. Just when we overlap the main area with the main threats, we see the fisheries are the most important: gillnets, purseines, and trawlers in the Mediterranean, gillnets and purseines in the Atlantic. We didn't analyze the traditional artisanal long-line fisheries, which are known to have very dramatic events of mortality in the Mediterranean. But those small vessels, they don't have the AIS, the Automatic Information Tracking System, so that information is not available to analyze. And finally, when we overlap the key areas with the marine protected areas, we see that the key areas also in the Mediterranean and in the Atlantic is very, very poor cover for the marine protected areas, with approximately 20% of them. And just conclusion, global distribution, main concentration along the Iberian coast, but new expansion to the north and new areas to prospect in the Mediterranean. Habitat suitability, influenced by distance to coast, bathymetry, and sea surface temperature. Population trend, as I said before, declining in the core areas, insufficient increasing in the north that compensate the main losses. The fisheries are very important, but offshore wind farm, as in the previous slide, is said not very important, but because they are increasing worldwide and also in the north of Europe, where the species is supposed to be expanding, could be very important. And then there's insufficient protection with marine protected area, which suggests we need to improve the areas, update it, and maybe expand it. And sorry for the time. Thank you.
Thanks.
Good afternoon, everyone. My name is Nicolas de Almeida E Silva. I am a PhD candidate at Deakin University in Australia, as well as La Rochelle University in France. And I will talk about my work on passive acoustic monitoring to reveal environmental influences on breeding short-tail shearwaters. So very quickly, short-tailed shearwaters is a species of seabirds breeding southeastern Australia, counting more than 20 million breeding individuals. It has a strong influence on its environment, and in return, the environment can influence its population. Because they're breeding and foraging in one of the fastest forming marine areas in the world, understanding their demography and their population trend can help us to understand and predict adaptation of seabirds to climate change. But the real challenge here is to be able to monitor the demography of short-tailed shearwaters because the individuals are coming back at night on their breeding site. They are coming in big groups and they're breeding underground in burrows, making any visual count impossible. But the short-tailed shearwaters are social and they are quite talkative. So instead of counting them, we can simply listen to them with the simple ideas that the more birds there is, the noisier it gets. So I'm using passive acoustic monitoring. I'm deploying song meters in colonies at night to record the acoustic environment. And then I process the data according to the short-tailed shearwater specificities. So I'm looking at the data 2 to 1 hour before sunrise, which is when the birds are calling the most, before going at sea. And then I'm filtering the frequency to match the frequency range of the call. And I'm filtering the lowest frequency to not get polluted by wind and waves, and the highest one to not get polluted by other sound, like a cricket, for example. And so in the end, I obtain my cumulative sound intensity, which is my short-tailed shearwater's bioacoustic index. And it worked great. I obtained a great linear relationship between my the bioacoustic index and the density of occupied burrows. So I can actually have the population trend over the years, which is fantastic. But there's actually way more than this in the passive acoustic monitoring. So this is the bioacoustic every night for a full breeding season. And at first, it can look a bit messy. But if I use the smoothing function like a GAM, some very strong patterns reveal, which are very well-known behavior of the short-tailed shearwaters. So the birds are arriving in October on their breeding sites. They dig their burrow, they bond with their partner. Then they're all flying to Antarctica in November for their preying exodus. When the birds are coming back end of November, the female will lay the egg and fly back to Antarctica, while the male will start the incubation shift. And when the female comes back from Antarctica, she gets on the egg and the male goes to Antarctica. And they keep shifting like this until the chick hatch. See the overall pattern. And so then after that, you have the chick rearing period where the parent starts to be less synchronous because the chick can stay alone for an extended period of time. And then the birds are leaving their breeding site end of March. So now that I have this index, I can look at different years. So this is Canada Island on an 8 years period. And we can see that we have some strong consistency, like the egg laying date is very consistent and very reliable, but also a lot of variability, like in the number of incubation shifts and their duration, as well as the timing and duration of the preying exodus. So I'm currently working on environmental variables, trying to understand if some of them are linked to this variations in patterns, dates, and duration. I didn't find anything yet, so I'm leaving you on a very exciting suspense. I didn't really prepare a conclusion slide, but I guess the take-home message is that passive acoustic monitoring does work very well to monitor seabirds with the right processing of the data. And not only does it give me my population trend, but it can also show me some very important information on the behavior of the birds in the context of climate change. Thanks. Thanks, everyone. Yeah.